Now, when we're adding and subtracting radicals, one thing that you have to remember is the number under the radical sign must be exactly the same. Remember, that's called the radicand. Must be the same in order to add radicals. Let's look at our first example. Here we're going to add 7 times the square root of 11 plus 4 times the square root of 11. Now, since these radicals are exactly the same, it's as if we are adding 7x plus 4x. The variables are the same. Now remember the rule, when we're adding like terms, we add numerical coefficients. 7 plus 4, that would be 11x. Now just as this is 11x, if I'm adding 7 root 11 plus 4 root 11, it's simply 11 times the square root of 11. Notice the radical portion does not change, just like the x's did not change when we added like terms. Keeping that in mind, let's look at our second example. Now we're going to add here 3 root x minus 2 root xy minus 5 root y plus 7 root xy. Again, what we're looking for is radicands that are exactly the same. If they are the same, they're considered like radicals, and we can combine their coefficients. So I have the square root of x. I have no other radicand that's exactly the same, so it will not combine with anything else here in my expression. What I like to do to keep track of what I've used, I like to cross things out as I use them, and then at the end I'll know that I include these in my final simplification. Now I see here I have the square root of xy. Square root of xy, that doesn't quite match, but look here down at the end. I've got negative 2 times the square root of xy and 7 times the square root of xy. Again, combining these coefficients, negative 2 and positive 7, positive 5. So that tells me I have 5 of these xy's. Cross those out because they've been used. Now finally, all I have left is minus the square root, minus 5 times the square root of y. So I just tack it on the end. Again, just make a quick check, make sure that all these radicands are different, which they are. Since they are different, we know that we cannot combine any further. Now, that was working with some radicals that were already in simplified form. What happens when they're not in simplified form? Well, what happens in that case is we have an additional step. We must start by simplifying each of our radicals. So let's look at our second example. Square root of 50 minus the square root of 18 plus the square root of 98. Now, looking at this problem, you can identify right away that all these radicands are different, so we cannot combine them in this form. What's hiding inside each of these radicands are factors that are perfect squares. Now, the more you work with this, the more you'll be familiar with the perfect squares, and the easier it will become. So don't get too frustrated up here at the beginning. When I see 50, I think of the largest perfect square that's a factor of 50. In my mind, I think 25 times 2. So I'm going to write the square root of 50 as a product of 25 times 2. Why do I do that? I do that because the square root of 25 I know is 5. So the square root of 50 simplifies down to 5 times the square root of 2. Now, believe it or not, but as you work more and more with these radicals, you'll just look at the square root of 50. In your mind, you'll think 25 times 2, and you'll come right out with 5 root 2. If that sounds impossible at this point, just wait and see. You'll believe me. Let's go on. Minus the square root of 18. Now, when I see 18, the largest perfect square I know that's a factor of 18 is 9. So I'm going to rewrite the square root of 18 as 9 times 2. Why do I do that? Again, because I want perfect squares that are factors, so I can simplify the perfect squares. The square root of 9 is 3, so that middle term, the square root of 18, simplify down here to minus 3 root 2. Finally, I have the square root of 98. And as I said, the more you do this, the more familiar you'll be with the perfect squares. 98 happens to be the square root of 49 times 2. You can check my multiplication if you want. Now, why do I choose 49? Because I know the square root of 49 is 7. And that tells me that the square root of 98 can be written more simply as 7 root 2. Now look what magically happened here. What I did when I simplified those first 3 radicals, under the radical sign, I got radicands of 2. Since they're all 2, they're all considered like radicals, therefore I can combine them. 5 minus 3 is 2, 2 plus 7, 9. So I can write this total as 9 root 2. Who would have thought by looking at this original expression it would simplify all the way down to 9 root 2? Let's try one more of these. Let's look at a little bit more complex looking expression. Let's throw in some variables with our numbers. Let's say we have the expression 2 root 12x minus 3 root 45x minus 3 root 27x plus 120. Now, don't be afraid of the looks of this particular problem. We're going to use the same procedure we did in the previous examples. We notice right away that these are all very different. What we're going to do then is we're going to look to see, are there any factors of the radicands that are perfect squares? In this case, I see that 12 has a factor 4, which is a perfect square. So I'll rewrite this as 2 times the square root of 4 times the square root of 3x. Now, if you're a bit confused, let me show you where this came from. 12x is 4 times 3x. Why did I choose to separate it in this particular fashion? The reason why is because the square root of 4 is a perfect square. It's 2. The square root of 3x is not a perfect square, and I know it's going to stay under the radical, so that's why I put the 3 and the x together under one radical sign. Now let's continue. I've got 45. Think of a perfect square that's a factor of 45. Do you come up with 9? This is the 3 that's out front. We're going to rewrite 45x as the square root of 9 times the square root of 5x. Again, the reason is because the square root of 9 is going to simplify down to 3. The square root of 5x, not a perfect square, it's going to stay under the radical sign. Now let's continue. Using the same procedure, we're going to rewrite 27 as, are you getting it? 27 is 9 times 3. So the square root of 9 times the square root of 3x. Finally, we have our last number, 120. So we have to ask ourselves, what number times 120, or excuse me, what factor of 120 is a perfect square? Well, right off the top of my head, I can think of 120, perfect square, 4. 4 goes into 120. So we're going to take this as a separate problem here. If we have 120 and we break it into 4 times 30, does that work? 4 times 30, 120. The square root of 4 is 2, so it's going to simplify down to 2 square root of 30. So let's go ahead and write that. And, oops, not equal, sorry. That's a plus 4 square root of 30. Square root of 4 times the square root of 30. Now, let's go back and rewrite all the perfect squares. The square root of 4 is 2, so this becomes 2 times 2 times the square root of 3x minus 3. The square root of 9 is 3 times 3 times the square root of 5x minus 3 times 3 times the square root of 3x plus 2 times the square root of 30. Now the square root of 30 does not have a factor that's a perfect square, so even though that's a rather large number, it stays as our radicand. Now what do we have? The outside numbers, 2 times the 2 that was there, give us 4 root 3x minus 3 times 3, 9, root 5x minus 3 times 3, 9, root 3x, and finally, down here at the end, we still have this 2 times the square root of 30. Finally, our last step is going to be to combine like terms. Remember, like radicals are those who have the same exact radicand. I can identify 2 of those in this expression, the first and the third. So that means I can combine them. 4 minus 9 is negative 5 times the square root of 3x. Notice these radicands are different from each other and from the first one, so they remain separate. Minus 9 times the square root of 5x times the square root of 30. So we can say, now you may not feel that good about this one, but this rather complex expression simplified to a less complex expression down here. Minus 5 times the square root of 3x minus 9 times the square root of 5x plus 2 times the square root of 30. The key to these problems is looking for factors that are perfect squares, looking for factors of the radicands that are perfect squares, and making sure that when you choose that perfect square, it's the largest possible.